Welcome to the deep dive. Today we're jumping into, well, one of the most intellectually ambitious, maybe even jarring interpretations of quantum mechanics out there.
It really is. It challenges everything you think you know about reality itself.
We're diving into Hugh Everett III's theory of the universal wave function, which, most people today know as the many worlds interpretation.
Right.
So our mission here is to get a real, solid conceptual grip on this. Whatever it was proposing was, nothing less than a complete, objective, and fully deterministic model of the entire universe.
And this is the key part, a model that includes us, the observers, without completely falling apart into paradoxes.
Okay, so let's start there. Why did the old model fall apart?
Well, the traditional quantum theory, the one most people sort of learn about, has this fundamental dualism. It's almost schizophrenic.
Right.
On the one hand, you have whatever it calls process two. That's the beautiful, continuous, deterministic evolution of the quantum state. Everything is governed by the Schrödinger wave equation. It's all smooth sailing.
Causal, predictable.
Perfectly predictable, but then you decide to look at it. You make a measurement.
And everything changes.
Everything changes. Suddenly you invoke process one. This is the instantaneous, totally discontinuous, and probabilistic jump. People call it the collapse of the wave function.
So the smooth wave of possibilities just snaps.
Snaps into one single outcome. And the theory never tells you why or when or what physically causes it. It's like this random external rule. And if you try to apply that rule to a system that actually contains the observer, well, the whole concept just eats itself alive.
Okay, so that's the crisis. So Everett's radical solution, he called it Alternative 5, was to just get rid of the collapse, get rid of process one entirely.
Exactly.
That sounds almost too simple, but hang on, doesn't process one, the collapse, give us all the quantum weirdness, the uncertainty? If you eliminate it, where does chance go?
It doesn't go away.
Gosh.
Its role changes. The core premise for Everett is that the state function, the psi, is the one true objective thing. And it always obeys the deterministic wave equation, process two, no exceptions.
So measurement isn't special.
Not at all. A measurement is just a physical interaction. It's the object you're measuring interacting with the measuring device or, with you. It's just two physical systems becoming correlated, becoming linked.
Okay, so let's walk through that. I am about to measure a particle spin. Its wave function is a superposition. It's both up and down at the same time.
Right.
In the old model, I look and poof, it becomes up. But in Everett's model, the wave function doesn't collapse. So what happens to me?
You become part of the superposition. The total system, that's you plus the particle, it evolves deterministically into a correlated state.
Meaning
Meaning the new state is a superposition of two distinct possibilities.
Wow.
In one part of that superposition, the particle is up, and a version of you has a clear memory of seeing up.
a version of me.
And in the other part of the superposition, the particle is down, and another version of you has a clear memory of seeing down.
So I'm splitting.
You are. The universal wave function itself just continues on, perfectly continuous and causal. But for the observer inside each of those branches, the process subjectively appears to be a random collapse.
Yeah.
It feels like chance, but the math just shows it's a branching.
Wow. Okay, that moves the uncertainty from the physics of the universe to the experience of the observer.
Precisely.
In this whole deterministic splitting thing. It was necessary because of the paradoxes that pop up when you have more than one observer, right?
Yes, exactly.
Yeah.
This is where the old theory really breaks down.
So let's talk about that thought experiment, the one that's a bit like Wigner's friend.
Yeah.
You have observer A sealed in a totally isolated room doing a quantum measurement.
Right. And from A's perspective, the outcome is random, a classic process one collapse. They write down spin up in their notebook.
And then you have observer B, who is outside the room, and B has the complete wave function for the entire room. That includes A, the lab equipment, the notebook, everything.
And B just lets the whole system evolve, according to the deterministic laws, process two. B can, in theory, calculate the exact state of the entire room a week from now.
So B's calculation would tell them exactly what A's notebook says.
If the old theory holds, yes. Which means A must have been wrong about the outcome being random in the first place. But here's the really bizarre part.
Go on.
If B then opens the door to check the notebook, the standard interpretation implies that B's act of looking is what collapses the wave function of the whole room.
So A's memory, A's experience of seeing spin up, it wasn't even real until B opened the door.
It implies that A's objective reality was somehow held in limbo, waiting for B to decide it. It's a massive violation of, objectivity.
Yeah.
It basically says my consciousness creates your reality.
Which is not a great foundation for physics.
It's a terrible one. It violates whatever it calls the principle of psychophysical parallelism, the idea that observers are just physical systems and should obey the same laws as everything else.
So Everett's model avoids that completely.
Completely. A's observation causes A to split. Later, when B looks, B also splits, becoming correlated with A's results. You get a complex superposition of a B who sees A saw up and a B who sees A saw down. Nobody's reality depends on anyone else's observation.
It's all just correlation. The universe isn't collapsing. You are splitting into correlated versions of yourself.
That's the takeaway.
Okay, so if this all hangs on the idea of correlation instead of probability, the math has to be pretty solid.
It does. And Everett actually borrowed a lot of his mathematical language from a different field that was booming at the time, information theory.
From Claude Shannon.
The very same. Everett started applying concepts like information and correlation directly to the wave function amplitudes.
So what does correlation mean in this context?
You can think of it as a measure of dependency. How much do you learn about system X by looking at system Y? And he proved, mathematically, that once two systems become correlated, you can't undo it. That knowledge of their dependence never decreases. It gets locked in.
That actually sounds a little familiar, like something from classical physics.
It's a great analogy.
With, say, a box of gas. Liouville's theorem says the total information about all the particles, their exact positions and momenta, is always conserved. It stays constant.
Right, but what happens to the individual particles?
They fly all over the place, the system gets more chaotic, entropy increases. Your information about any one specific particle's position gets worse and worse.
Exactly. That marginal information, as it's called, decays. But, and this is the beautiful part, that loss of information is perfectly balanced by an increase in the total correlation information between all the particles.
So the more random the parts look on their own,
the more tightly linked their fates become as a whole.
And that connects back to quantum mechanics. How?
The universal wave function is like that box of gas. It's always spreading out into this massive superposition. But the strengthening of correlations between you, the particle, the measuring device, that's what locks you into a subjectively consistent branch. Your reality is defined by what you are correlated with.
Wow. Okay. So this focus on correlation, it seems like it would solve a lot of other quantum headaches, too.
It does. It gives the theory a huge operational strength. Take multiple observers, for instance. If you and I both measure the same particle separately, and then we meet up to compare notes,
Might have to agree, right?
the theory proves you will always agree.
Yeah.
The consistency is baked into the correlations of the total wave function. The branches where you see up and I see down they don't exist.
And what about something really spooky like the EPR paradox? Entanglement.
It gives a really simple, I'd almost say easy explanation for it. You measure one entangled particle here, and its partner far away seems to know instantly.
Action at a distance.
But in MWI, there's no action at a distance. Your local measurement just correlates you with your nearby particle. And because that particle was already entangled, already perfectly anti-correlated with the other one, you are now automatically correlated with the remote particle as well. The branching is local, but the dependency was there from the start.
So it's not spooky, it's just a necessary consequence of the math.
It's just math.
Okay, but there's still the biggest question of all for me. If everything is this constantly diffusing, branching wave function, why does the world look so solid? Why isn't my coffee cup smeared out across the room?
The cannonball problem. Schrödinger worried about this exact point.
Right. Why don't we see superposition in our macroscopic world?
The answer, again, is the incredible power of correlation laws. A cannonball is made of, trillions upon trillions of particles.
It's an unimaginable number.
And while the wave function for the cannonball's center of mass does spread out over time, the relative positions of all its constituent particles are held together by incredibly strong internal correlations.
The force is holding it together.
Exactly. So the total state isn't a smeared out goo. It's a superposition of many distinct cannonball states. Each element of that superposition describes a perfectly solid-looking cannonball in a slightly different but definite position.
So classical reality, solid objects, they just emerge.
They emerge as a feature of the intense correlation between all the constituent parts. Correlation is what makes the world look solid and behave classically, at least to us.
So to bring it all home then, Everett's big claim is that the probabilistic rules of quantum mechanics, that whole process one thing, they aren't some new fundamental law of nature we have to add in.
Not at all. They're deducible. You can derive them from the pure deterministic wave mechanics alone. They only appear at the subjective level of an observer who is part of the branching process.
That's a powerful idea.
It's incredibly elegant.
Yeah.
You end up with a conceptually simple, complete, and logically consistent model of the universe. It's all based on one thing, a universal wave function that always obeys one simple linear equation. It puts the observer back inside physics, and it satisfies Einstein's famous demand.
God does not play dice.
In this model, he doesn't. The universe is deterministic. The dice throwing is just an illusion created by our own branching perspective.
But it's an illusion that forces us to accept an unbelievable number of other worlds, other versions of ourselves. And so the final question for you, the listener, is this. If the single probabilistic reality you perceive is just an appearance, an artifact of correlation in a deterministic branching universe, what does that say about the reality of all those other versions of you, the ones living in the branches you're not currently experiencing? Is the uncertainty you feel real, or is it just the price you pay for being part of the correlation?